Hello, everyone. My name is Giovanni Cuevas, and my teammates were Kunal Shenoy and Shivang Patel. Our project focuses on automatically pulling key concepts from educational texts, specifically machine learning chapters, and using those to build concept maps to show how ideas are connected. To split up the task assignments, Shivang took the lead on developing the actual extraction algorithms. That includes both the traditional methods and the deep learning based models. Kunal managed the timeline and made sure all model outputs stayed consistent across different chapters. He also helped us keep everything organized for the final report. I focused on the presentation and helped with reviewing and debugging code in Colab. I also worked on writing and editing sections of the report to make sure everything aligned with our goals. As a group, we stayed in touch through weekly check ins and used shared tools like Google Drive, and Colab to collaborate smoothly. To build our approach, we looked at a lot of existing work in this area. Traditional methods like TF, IDF, and TextRank use statistical or graph based techniques. They're fast and simple, but miss deeper meaning. Then we have supervised learning models like KEA, SVM, and CRF. They can be more accurate, but they need a lot of labeled data, which isn't always practical. A big shift came with pre-trained models like BERT. We looked at models like CIF and BW rank, which use BERT embeddings to capture context. One of the newer ideas we explored was using multiple BERT layers instead of just the last one. Each layer captures different linguistic info, so combining them boosts performance. For educational application, there's a method called FACE that extracts concepts from textbooks to support personalized learning, similar to what we were trying to do. But there are still challenges, like domain specific limitations, evaluation inconsistencies, and the usual balance between precision and recall. Now let's talk about the intuition behind the method. TF, IDF, and Rake are kind of like frequency detectors. They find words that appear a lot in chapters, but not in every chapter. That makes them fast and easy to work with, but they don't get the meaning. So something like decision tree might be treated the same as tree structure, which obviously isn't ideal in technical content. That's why we brought in BERT-based methods. With BERTner, we use pre-trained model to spot named entities, things like algorithm names or model components, even if they don't appear super often. Then we use fine tuned Cyber, which is trained on scientific data that gave us more accurate concept boundaries and better recognition of technical phrases like gradient descent or loss function. To connect the concepts, we used co-occurrence, meaning if two concepts show up in the same sentence a lot, there's probably a connection. And by visualizing those connections, we built a concept graph that helps learners understand how topics relate to each other.
My name is Kunal Shenoy, and I'm going to walk you through our methodology for this project. We tried 4 different extraction approaches, starting with TF-IDF and logistic regression, moving on to Rake, then BERT-NER, and ending with fine-tuned Cybert model. For our feature engineering, we used TF-IDF features of word and phrase frequency scores, n-grams, and document frequency constraints. Our handcrafted features consisted of term frequency, phrase length, word length, and verb initial phrases, and our BERT features consisted of contextual embeddings, NER tags, and token level classification. For our TF-IDF approach, we used spaCy for tokenization and noun phrase extraction via pattern matching. We combined TF-IDF vectors with handcrafted linguistic features and applied a logistic regression classifier trained on our index terms from the training chapters. With our Rake approach, we used NLTK stopwords to identify phrase boundaries, and we scored phrases based on word frequency and co-occurrence. We applied thresholds and filtering and selected the top 300 phrases. With our BERT-NER approach, we used a pre-trained BERT-based NER model and processed text sentence by sentence to identify named entities. We extracted unique phrases of 1 to 5 words after filtering and normalization. For our fine-tuned Cybert model, we created a token-labeled dataset matching index terms to tokens. We fine-tuned a Cybert SciVocab uncased model with the custom label set and applied it to test chapters to identify domain-specific key phrases. Our relationship identification was done through co-occurrence analysis of key phrases and sentences, and our edge weights were based on co-occurrence counts. We used Network X for our concept graph visualization. Moving forward, we're going to see each of the four approaches with a table followed by a graph, starting with TF-IDF. So as expected, a linear regression model is not the ideal case for this task. We can see there's about a 16% precision in identifying concepts with a recall of 22% and an F1 score of 19. It struggles to tell you what is a concept, but it can tell you what isn't. Moving on to the map, we can see the suboptimal quality in our phrase selection for this approach, with many of the nodes not consisting of true index terms. Additionally, we see the first downside in our methodology for relationship identification. Co-occurrence can be helpful in building general buckets for our terms, but on its own, it is not the ideal scenario for capturing semantic relationships. We're exploring other methodologies and combinations of features for this task, but for now, this is what we're using. Rake did not hold up well either, returning 833 false negatives and only 214 true positives at a precision of about 71% and a recall of about 20%. Here we can see the second downside to our co-occurrence analysis for relationship identification. Rake's partial matching and low accuracy caused significant issues in developing a proper co-occurrence analysis and the relationships between them. With BERT-NER, we're starting to see significant improvement in reducing our false negatives down to 184, but we do see a higher rate in our false positives. As far as the concept map goes, despite its precision, BERT-NER held up pretty well, and it's reflected in the node selection and the relationships in this map. We still need to work on reducing duplicates like tree versus trees, but general relation and term identification was reasonable. We got our best results out of Cybert. A quick explanation of the labels in our dataset. We're looking to see if the term is outside of a key phrase, that's our O, if it's at the beginning of a key phrase, that's our B concept, or if it's within a key phrase, that's our I concept. So we can see some fairly significant high precision recall and F1 score across the board. We trained this model on our dataset over 8 epochs. And moving on, we can see that our index term identification is significantly better with Cybert, as seen on the map, although the visualization does suffer from the same problem as the others. Everything is tight, but we can see each node does contain a true index term from one of our chapters.
My name is Shivang Patel, and I'll talk about the lessons that we learned and key takeaways from this project, along with the limitations, the challenges, and the future work. So, one of the biggest things we learned from this project is that deep learning outperforms traditional models like TF-IDF and Rake when it comes to extracting key ideas from educational text. These older models are fast, but they rely mostly on how often words appear. Deep models, on the other hand, actually understand the context, which makes them more accurate, especially with technical or complex language. Another thing that we learned was that our fine-tuned Cybert model outperformed every other model that we used in our project in terms of both precision and recall. It was extremely accurate and extracted almost all of the important phrases from the chapters. And since Cybert is trained on scientific writing, it really handled the vocabulary and style of the chapters really well. So it is an extremely powerful model to use for domain-specific tasks such as this project. One of the key takeaways is that Bertner, while it wasn't as accurate as Cybert, it was really good at extracting a lot of key concepts. The recall score was 0.82, so it is a good model to use if you're looking to extract as many relevant ideas as possible. And it is not computationally expensive as Cybert, so it is a good model to use. As Giovanni mentioned in the beginning of the presentation, that we use co-occurrence to figure out how concepts were related, just to check if two key phrases showed up in the same sentence. And what we learned from that is it works surprisingly well. It gave us a way to connect ideas and start building a concept out without needing any manual labeling or deep analysis. Another key takeaway from this project is that we can feed an entire chapter and it can automatically generate a concept map using NLP pipelines without requiring, again, manual labeling or editing. Now on to limitations and challenges. One of the limitations was that we only tested chapters in this book. We didn't test it on other books or chapters yet, which will be our future work. But as of right now, that this was our limit, so we don't know how good our pipeline really is. One of the challenges that we encountered was how we evaluated our models. We used exact and partial string matches, which is okay, but not perfect. Sometimes the model grabbed a phrase that was right, just worded differently than the textbook index, but it didn't count. So we probably underestimated how good some of our models actually were. Another challenge was ambiguity or overlapping phrases like gradient descent or stochastic gradient descent. These models sometimes got confused about where one phrase ends and another begins. It's a tough problem, and it made training and evaluation a lot trickier than will be expected. Another limitation is that training these models took time and power, especially Cyber, which requires a lot of GPU time, and we were using Google Colab, which has limited GPU options and computing time, unless we upgraded to Colab Pro or Colab Plus, which we didn't want to, so the training time and power was a limitation for us. Lastly, our relationships between concepts were only based on sentence level co-occurrence. That's a decent start for our pipeline, but it doesn't tell us if one concept causes another. So if it's a part of a larger category, we definitely want to go deeper with that in the future. Like I mentioned in the previous slide, we didn't test it on other books or chapters, but one of our future works includes to see how our pipeline performs on other books and chapters, and we want to pick books that are in different subjects, such as like biology, economics, or maybe even non-English textbook. That will really help us figure out how flexible and reusable our pipeline really is. Also, for concept relationships, we're looking into using graph neural networks. These models are designed to handle complex relationships in structured data and could help us find more meaningful, deeper connection between ideas, which are way beyond just sentence level co-occurrence. Another idea we had was to integrate external resources like WordNet or ConceptNet. These knowledge base bases can help us verify concept, avoid a duplication, and even connect them to bigger ideas outside the text that could make our concept map more powerful and reliable. Lastly, we would love to turn this into an interactive tool, something students could use to explore topics visually, click into concept, and even follow personalized learning path because we think it would be a really cool way to study. And yeah, those are our future works.